Before we begin, we'd like to thank our project partner, Dr. Phil Tuma at the Matcha Mission Hospital, as well as our project manager, Dr. Emily Ferrer, and our technical advisor, Dr. Matthew Ferrer, for leading the team and making our project possible.
So I had the opportunity to spend a portion of last summer living and working and learning in Matcha, Zambia, as a member of the Diagnostics for Viral Diseases collaboratory team. Unfortunately, rural and under-resourced areas in sub-Saharan Africa, places like Zambia, are plagued with high prevalence of infectious diseases, and HIV is the most prominent in the Matcha area. However, the clinical laboratory setups that are needed to house these instruments that are used for these diagnostic viral load tests are only found in major health clinics, and as a result, patients in the rural areas have difficulty obtaining this kind of quantitative diagnostic information about their health. And so getting appropriate treatment becomes a challenge. In the Matcha region, the current diagnostic instrument that is used is housed in the Matcha Mission Hospital. And although smaller rural health posts exist in the region, they're often just small concrete structures with no electricity or running water, and they're only manned by a nurse or maybe a few volunteers. And so consequently, many patients in the surrounding area have to travel up to 20 kilometers by foot to Matcha if they're to receive quantitative diagnostic tests. And so this is why we're partnering with Dr. Phil Tuma and the Matcha Mission Hospital as we work to develop a portable viral load diagnostic tool that would bypass the need for expensive laboratory setups in under-resourced rural health posts and hopefully make viral load tests more accessible to patients in that demographic.
In order to achieve the goals we had set out to get to, we realized that our device would need to have a couple of design constraints applied to it. The first of which was that the device would need to be sensitive enough in order to detect the viral load count with a high enough precision. We determined that this load count would be 1,000 viruses per milliliter, simply because this is the viral load count at which doctors tend to change treatments. We also figured that our device would need to be cheap enough in order to be affordable to the Matcha Hospital. For that reason, our goal for this device is to ensure that it costs no more than $2,000. Each test would also have to be cheap enough, and so the constraint for that would be $10. We also figured that these tests would need to be run quickly in order to ensure that the patient could get them without needing to go home in between, which could be a process that might take several days. For that reason, we decided that our device would need to be able to run the test and complete it within 1 hour. Finally, we wanted to ensure that our device would be portable to ensure that they could be taken to rural clinics and be used wherever necessary.
So to obtain an HIV viral load count from a blood sample, our system takes advantage of a fluorescent probe that we designed to tag itself to the GP120 protein that presents itself on the surface of the HIV virus. And so within our optical setup, the sample is then interrogated by a laser beam, which excites the probe at a specific wavelength and emits photons that correspond to the amount of virus particles that are present. And so the photons are detected on a silicon photomultiplier, or SIPM, and the signal is processed and interpreted on an FPGA and CPU unit that is on a small chip. This is processed and displayed on a small LCD screen, and the readout is in the form of a numerical value of viruses per milliliter and a graphical representation of the viral count. And so this can be used in clinical decision making.
Fluorescence correlation spectroscopy, or FCS, is used to detect and calculate the number of fluorescent particles in a sample, in our case, the probe that we use to bind to the outside of HIV. To do this, we use a laser to excite the sample, and when the probe travels through that laser beam, it emits a light back that we can use to detect and calculate the number of viruses in the sample. And now you're going to be shown a video of just how we use this setup in our lab. Once we can verify that this larger exploded prototype works with our fluorescent probe and with the rest of our system, we can work on condensing it into a portable system. Now Brant is going to talk to us about just how we can turn the signal coming out of this device into a viral load count using an autocorrelation function.
To generate the FCS decay curves, we're using something called an autocorrelation function. which is basically analyzing the stream of photons to determine how related they are to one another. Originally, we were doing the autocorrelation on a PC using Java, but that posed a number of problems for us. First of all, PCs are expensive. Second, PCs that are powerful enough to do the autocorrelation in a timely manner are generally pretty large, which hurts our portability. 3, PCs use a lot of electricity, which makes it less easily powered by a battery. And 4, even on a PC, it was taking a few minutes to complete the autocorrelation, which is okay but not ideal. So that caused us to move over to something called an SoC, or a system on a chip. And so a system on a chip has a CPU part that can do general operations, but it also has a digital building block side, kind of like a digital Lego bin, where you can use those digital components to build specialized hardware to do one job and only one job really quickly. And so we built an autocorrelator in an SoC. The autocorrelator is much faster in an SoC. It actually runs in real time now. It's very small, it's lightweight, it uses a small amount of power, and it costs about 1/4 of what a PC costs. The downside is it is quite complex to design for SoCs, and so that's our main challenge. But as engineers, it's our job to take the challenging and complex systems, integrate them together, and make them usable so that the everyday person can use them. And that's where Nathan comes in.
As the final step in the process, the CPU in our device performs the final calculations necessary to deliver the viral load results we are looking for. Once the FCS decay curve data is received from the FPGA, we extract several parameters from the data by fitting it to the known formula for an FCS decay. Compared to the autocorrelation analysis, this step requires relatively few resources, so the CPU is capable of performing it. After speaking with some technicians at Matcha, we also determined that a simple and easy to use UI would be preferable over a complicated but flexible one. As such, we designed our interface around the basic elements necessary for the device to perform its function. This meant making the viral load as prominent as possible, while simultaneously accompanied by a graph that allows technicians to verify the validity of the test. Additionally, we have hardware buttons on our device that get mirrored on the screen, allowing the technician to give the necessary commands to the device in a simple and efficient manner.
Originally, our team's goal was to have an exploded prototype functioning by the end of this semester. However, due to the coronavirus pandemic, this was not possible. Instead, we now plan to push back that deadline to next semester, fall of 2020, for the functional exploded prototype. We appreciate your time and your interest in this project. Thank you.